Good morning, good afternoon, or good evening. This is going to be a full paper work through of the June 2022 Further Maths Paper 1. Aim here is to not only give you something to help you review your own work, to mark your own work, but also to show off some of the thought processes, the exam techniques, etc., when tackling such a paper. So we need our humorous name. I'm going to be Mark Solutions, a good instruction as well as an amusing first name, surname combo. So we're going to jump straight in. We have a displacement of a particle from its equilibrium position. It's x. The motion is given by that. We should recognize this immediately as simple harmonic motion. Calculate the period of its motion. So our formula is t equals 2 pi over omega. The omega is, well, omega squared is the 9. So that's going to be 2 pi by 3, which matches that answer over there. You can see them trying to be sneaky if you didn't remember the squared or you didn't remember the 2 pi, then they've got all those traps set up and waiting for you. Question 2. Simplify that. So probably the simplest way to tackle this is by remembering the exponential form. So this is e to the 6 pi I by 13 over e to the, well, we need to watch out for that minus sign there. So that's e to the negative 2 pi I by 13. Subtract the powers, e to the 8 I pi by 13, which goes back to that form there. Alternatively, you could have remembered just that when you divide, you subtract the arguments. So that's where we get the 6 pi over 13 minus the negative 2 pi by 13. Question 3. Given that y equals sech, so we're trying to differentiate 1 over cosh. Lots of different ways to tackle this. I'm going to think of this as cosh to the minus 1. But you could have done it as a quotient rule as well. So that's going to become, bring down the power, reduce the power by 1, and times by the derivative. So I've got a shine going on. So probably the best way to write this is negative. I've got a shine over cosh, which is a than, and I've got a 1 over cosh. This is a sech, so I'm looking for negative sech tan, which is right there. The vector v is an eigenvector with an eigenvalue of 4, so nv equals 4v. Vector m is also an eigenvector, mv equals 3v. So then if we put all that together, each m pops out a 3, each n pops out a 4, so this is going to be 3 squared times the 4v, so that is 36v, which is quite nice. If you've got eigenvectors, then the product of those matrices are also eigenvectors, which is the product of the eigenvalues. Question 5, we're given that that is a root of that equation. Where k is real, find the other 3 roots. So straight away we can get a second root from the fact that this is a real cubic, a real quartic. So we can just have the complex conjugate as the second root. Now to find the other 2 roots, I'm actually going to try and find the quadratic, which has these 2 solutions. So I'm going to call this one alpha, I'm going to call this one beta, and try and find the quadratic with roots alpha and beta. easiest way to do so is to take the sum, which is -3, and the product, which is going to require a little bit more working. 9/4 plus 11/4 is 5. So alpha and beta solve z squared plus 3z plus 5. So then my polynomial in z I can factorize as z squared plus 3z plus 5 and something else. To make the z to the 4, I need the z squared. That's currently giving me positive 3z cubed. So I want to lose 6z cubed. I'm going to cheat and jump straight to the back coordinate. I need to multiply to 40 at the back, 5 times something. I want to check the z squared term. The z squared term is 8 minus 18, which is minus 10, plus 5 is minus 5, which does match. It's a good little bit of exam technique there to check whichever level that you haven't used. And because I'm trying to solve this, I now want to try and factorize probably this back quadratic, which does factorize quite nicely. So my other roots, let's answer the question as clearly as possible. My other roots are the minus 3i minus 3/2 minus I root 11/2, and the two real solutions from the other two brackets, 4 and 2. Given that x is a real number, solve that quartic being negative. Okay, well, any inequality, and this is both a personal preference but a general hint, any inequality is really good to be solved by thinking about the picture. Now, this is a quartic, so we'll expect it to look like that, but it only has 2 real roots. So the quartic probably does something like this, with solutions of 2 and 4. And now it's really obvious where this quartic is below the axis, just between 2 and 4. Because it's a positive quartic, so it looks more like a W than an M shape. Question 6. Given that mod x is less than 1, prove that. Now we need that mod x is less than 1, because if you remember what the tan graph looks like, it's got those two asymptotes, so we can't invert anything outside that range. That might be useful as we go through the problem to pick a square root to be the right form. But the best way to tackle these is by setting y equals to rearrange and turn into exponentials. So we know that tan is sine over cosh, and I've written them both in terms of exponential straight away and cancelled the halves. And now we just need to try and solve this. And if you recall the similar methods for cosh and for sine, we're basically aiming for a quadratic in e to the y. So I've got an x, e to the 2y plus x here, and e to the 2y minus 1 there. And it's actually a very nice quadratic because there's no e to the y term. I'm going to have a quick look at the answer, and I can see in the answer that there's an x plus 1 and a 1 minus x, which is hinting that I should move the 1 over there and bring the x e to the 2y on this side. And this is going to allow that 1 minus x to appear much more clearly. Otherwise, I'll get an x minus 1 and have extra negatives that I didn't really want. So e to the 2y, I'm going to write the top as 1 plus x rather than x plus 1, because I know that's what the answer wants. Taking lens and dividing by 2 gives me the required form. It is a prove, so I'm going to write the conclusion. This is going to mean that tan inverse of x equals a half ln 1 plus x over 1 minus x. Nice and simple. Be warned that you shouldn't skip any steps on these kind of derivation style proofs. Useful things to do as well, like I've done up here, to signpost your working as carefully as possible. Moving into part B, solve the equation. Now, this is a part B, which implies that part A is actually relevant in some way. So part A has found tan inverse. So let's try and write everything in terms of tan. Issue is we've got sec squared. Now, if you've memorized all of those Pythagorean identities, good job. Otherwise, just remember one and go and rearrange to find the others. So that's the one that I remember. I want to sec, so I'm going to divide through by cosh squared. So dividing through by cosh squared gives me that identity, which I can now use directly into the equation. So that equation I'm now going to have as 20 lots of 1 minus tan squared minus the 11 tan equals 16. And again, exam technique, notice what I've done here. I've made it very obvious to whoever's reading my work where things have come from. So there's absolutely no doubt that I have chosen to go back to the original equation now in my working. And just simple signposts like that is incredibly effective in your work. This looks like a quadratic in tan, so let's make it look more like a quadratic in tan. I'm going to move everything onto one side. I want to make the tan squared positive. So I've moved that over. I'm going to move the 11 tan over, and I'm going to bring that 20 over to combine with the 16. Now does this factorize nicely? I can have a 4 times 4. Yes, it does. So I can have a 4 tan times by 4 to make a 16, but then I've got 5 tan to combine with the 1 left from the 4 to make a 5. I want to subtract off that 5, so on positive 16, subtract 5. So my solutions, tan equals a quarter or negative 5 over 4. Nope. Negative 4 over 5. I was kind of hoping that one of the solutions would disappear. Unfortunately, they don't. Both of these are within that mod x is less than 1. So I now need to use that result from part A. So part A is going to mean that x is a half ln 1 plus over 1 minus. For the quarter, I'm going to simplify this one before I go to the next part. So that's going to be 5 quarters over 3 quarters. So 5 over 3. Or a half ln 1 minus 4/5 over 1 minus 4/5, or 1 plus 4/5. So that's going to be a half ln. The top is a fifth, the bottom is 9/5 ln of a ninth. Yeah. And quite a nice solution there. And you can, with a question like this, use your calculators, sub that nonsense into the x positions and see if you get 16. Now, because they are exponentially hyperbolic, you might not get exactly 16 if your calculator does round poorly. But if you don't, you should get exceptionally close. And that'll be a good little check to see if you've done all this algebra correctly. Moving on to question 7. we have a matrix defined as so. Given M is a non-singular matrix, non-singular meaning we can invert it, we actually want to find the inverse. So to find the inverse, we need to do a couple of things. We need to find the minors, we need to find the cofactors, but we also need to find the determinant. So I'm going to start by finding the determinant. Now, having a look at that matrix, it doesn't look like there's anything particularly nice about any of the rows or columns, but I'm just going to do first column just to be a bit different. So the first column says 1 times the determinant of 6k plus 1, 3, 2. Swap the sign for the next component. So that's 3 lots of that 2 by 2 plus 1 lot of the 2 by 2 in the top right. So we get 12 minus 3 lots of, and this is now really careful algebra is all you need here, minus 3 lots of 14 minus 9, it's 23, plus 7 lots of k plus 1 minus negative 18, so plus 18. Let's expand and simplify. I might as well just expand everything first. 7 plus 18. Now I need to do the actual simplifying. I've got 4k's, got minus 72, and I'm adding on my 18 failed slightly, 25 and 37. So that's going to leave behind 35, negative 35. Not the nicest, and of course I'm cheating without using my calculator here. You should definitely be using yours to check your work carefully. So that's my determinant. Let's now find my matrix of minors. So minors are the 2 by 2 determinants left over. So we're going to need quite a large matrix here. We've already done some of them. If I ignore the 1, leaving behind the determinant there, that's going to be 12, that's going to be 9 minus 3k. The minor for the 7 is going to be 5 minus k. Determinant for the minus 3 is 9 minus 6. For the 3, we've already done that one. That was 23. For the 6 is 5. For the k plus 1, it's minus 4. For the 1, it's going to be 7k. We've got plus 7, that's plus 25. We're going to have k plus 1 minus 9, k plus 10. And finally, 6 minus 21. Why is that one making my brain go the worst? It's minus 15. And that appears to be my matrix of minors. So we can now do our cofactors and our M inverse. I personally prefer to jump straight to M inverse now, because the cofactors is just swapping some signs, and the final step is then the transpose. So I'm going to write out the matrix again, but each row is going to become a column, and I'm going to swap the signs in the 4 positions there. So going along the top row, writing down the first column, I swap the sign of the 5 minus k. The middle row becomes the middle column, and the final row becomes the final column. And there's lots of ways to check your work here again. You can do the whole multiplication, m times this, to see what happens. you should get the identity. Or, probably simpler, is to pick a random value of k, pick your favorite value of k and type it in your calculator, find the inverse of the matrix at there, and see if it matches the matrix down below with 0 subbed in. A very nice way, a smooth way to check you're working. Doesn't guarantee you've got it right, but it's as close to a guarantee that you can get that quickly. State any restrictions on the value of k. We said it was invertible, so the determinant can't be 0. The determinant was 4k minus 35. So k cannot be 35 over 4. Using your answer to part AI, solve that. Well, if I look back to the answer, the matrix looks similar. The first one is 1, 7, negative 3, 1, 7, negative 3. 3, 6, 6, we've got 3, 6, k plus 1. So that tells me that k is 5. And the final row, 1, 3, 2, matches perfectly. So first thing to do is to rewrite this as a matrix rather than as a simultaneous equations. So we're multiplying by x, y, z equals 6, 3, 1. So the x, y, z is equal to the inverse of that matrix, which we have over here. So subbing 5 into that, we get negative 15 as my determinant. I'm going to be a bit jarring as I swap forwards and backwards, I apologise. We have that k is 5, so negative 6. And then that'll be 0 there, won't it? Negative 6, 0, 3, negative 23, 5, 4, negative 23, 5, 4. And subbing 5 into the final column is going to be 7 times 5 plus 25 is 60, minus 15, minus 15. 60 minus 15 minus 15 times by 6, 3, 1. Now again, you can do this multiplication, at least check this multiplication in your calculators. So my top row, I'm getting a negative 36, negative 69 plus 60. Which the next, that's minus 9, that's going to be minus 45. I'm really happy because minus 45 is a multiple of 15. I'm dividing by 15 in a moment. 0, 5, negative 15 times by that gives 0. We've got 18 plus 12 minus 15 gives me 15. So my answer as a vector is 3, 0, negative 1. Question didn't involve vectors, so let's translate it back into an original set of solutions, 3, 0, minus 1. And I am going to very quickly check that they do match in here. So 3, 0, minus 1 is plus 3, does make 6. So the top equation works. The middle equation, we have 9 minus 6, perfect. And the final equation, we've got 3 plus 2 lots of minus 1, which is 1, perfect. And that's a beautiful thing about simultaneous equations. If they work in the originals, you must have got the answer perfect. Okay, carrying on, question 8. We have a complex number such that it is given that w is that. Find an equation for y in terms of x. So the argument of w plus 2i, which is x plus y plus 2i, And the argument of a vector is the inverse, the tan inverse of the opposite over the adjacent, which is the y thing, over the x thing, which is going to mean that y plus 2 over x equals a half, which I'd like to write as 2y plus 4 equals x by clearing the fractions. Now we do need to worry a little bit that we're in the right quadrant, but we're fine. We've got x as being positive, so we are in the right side of the picture. Tan inverse of a half is then saying we're in the top right side of the picture. The complex number satisfies both of these two things, and notice this condition here is exactly what we dealt with in the first part of the question, which means we know what the equation of that line is. It's a bit awkward because it's x equals, so I am briefly going to rewrite this in the other way round. So that'll be a half x minus 2. So there's my minus 2, and a half x, 2 across is 1 up. 2 across 1 up, 2 across 1 up. I've been way more accurate there than I probably need to be. So that is the upper bound for my angle. The lower bound is negative pi by 2. So if I'm starting there, negative pi by 2 is straight downwards. So I definitely shouldn't be feathering that line too much. So my complex number z just from that condition is somewhere in this region. We want the region of both conditions, so you now need to go for this one. So that's saying z minus 2 minus 3i is less than or equal to 2. So let's find 2 minus 3i is that point there. We have a radius of 2. Yeah. I was just worried for a moment, for no good reason. So I want to be drawing this circle very roughly, and I've aimed for those kind of 4 compass directions, 2 in each of those 4 compass directions to make my circle at least a little bit accurate. Now we want it to be less than or equal to 2, so I want to be inside this circle. So my region R is this region here. Notice it looks like the only bit missing is a tiny little slither here. Other than that, it's just a circle. So final couple parts, Z1 is the point which it is minimum. So we want to find the point in this picture where the modulus is minimum. Well, if we want to go into this region as small as possible, then we're going to have to hit this line here at a right angle. Is that correct? Yeah. Normally we go to the center, but the center's not quite in there. So the center's not perpendicular to the line, is what I mean. If we go directly towards the center, then you can see that that point there is slightly further away from the origin than going perpendicular to the line. So I want to find that distance there. Now, the one thing that's concerning me slightly, I could set up simultaneous equations here quite easily for those 2 equations. The thing is, it's asking me just for the modulus first, and then to find the actual coordinates, whereas that technique appears to find the coordinates first. So my next thought is there a right angled triangle? Well, there is a right angled triangle. Do I know enough of the side lengths? I certainly know that that side there is 2. I'm not convinced that there's another easy side length. So I'm going to do it the find the coordinates way first. Yeah. So we already have the equation of one line. So the equation of that first line was 2y plus 4 equals x, which had a gradient of a half. And the other equation, therefore, has a gradient of -2, and it goes through the origin. So I've got that set up. So that's going to mean subbing the y in, minus 4y plus 4 equals x. So x is 4/5, and y is -8/5. So the z1, and I've actually answered the next part of the question, is 4/5 minus 8/5 I. So the modulus of z1 is going to be 4/5 squared plus 8/5 squared, all square rooted. That's 16, that's going to be 80. So that's 4/5 root 5. A couple of tricks I use there, but again, just use your calculator. So then express z1 in the form. So z1 is 4/5 plus, nope, minus 8/5 I. Now, as I've got to this point in the question, I've now thought of another way we could do C part I. Maybe, because I know, or it appears, that that point is on that diagonal line there. I'm trying to think if I could have abused the fact that the argument is tan inverse of a half in some clever way. But that gives me this angle here. Yeah, I could have. So if I know tan inverse of that angle, then I know that this here is tan inverse of 2. If two angles add up to 90, then their tan inverses are reciprocal of one another, or their tans are reciprocals of one another. So that's tan inverse of 2. And if I know that angle, then I can use some trig to work out this side here. So yes, there was a triangle only approach to C part I, but I wanted to use simultaneous equations, and that's fine. Whatever method you see is probably the best method to run with, even if it's slightly less efficient. Roberto is solving this maths problem. We have a polar curve for all possible values of theta. Find the area enclosed by C1. He's integrated the r d theta, or r squared d theta, and got an answer of 0. Okay, so it looks like later part of the question we're going to explain what he does wrong. But for first, we want to sketch the curve. So we're trying to sketch r squared is 3 sine 2 theta. So picking some values, if we choose theta to be 0, then r is 0. When we pick theta to be pi by 4, that's going to be sine of pi, that's going to be out at 9. So I'm going to put a dot up here. When theta is pi by 2, sine of pi is 0 again. So I've got back to the origin. And then that seems to repeat. When I put in 3 pi by 2, I get -1. But when I put -1 in, I've got r squared equals -9. So there is no solutions when sine 2 theta is negative. So there's no solution between pi by 2 to pi. Is that right? So sine of 2 theta is, that was normally pi, but I've stretched it outwards. No, I've squished it inwards, sorry. So that there would be pi by 2 now. Yeah, between pi by 2 and pi, sine is negative, so there's no solution there. So I'm going to have that nice petal-like loop in that region. From pi to 3 pi by 2, I'm going to have the same out in that region. And again, from 3 pi by 2 to 2 pi, there's going to be no solution whatsoever. That point there is when r equals 9. R equals 9. And that's at pi by 4 and negative 3 pi by 4. A bit excessive on some of that labeling. But important is you get this double petal style picture. Explain what Roberto has done wrong. So in his integral, it's including the non-existent 2 branches. There are 2 branches which are kind of here, which will be contributing a negative area which don't actually exist. So his integral includes the branches, or is it pi by 2 to pi and 3 pi by 2 to 2 pi, which give r squared is negative and don't exist on the curve. So to actually find the area, let's split it into the 2 separate petals. So I'm going to say that the area is 2 lots of the integral between 0 and pi by 2 of a half r squared d theta. So I'm using exactly the same integral as he's doing, but I've chosen to only use a smaller region and therefore cut out the bits that the integral pretends are there but are not. So integrating this, integrating sine leads to negative cos. The 2.5 have cancelled. Cos of pi by 2 is negative 1. Cos of 0 is 1. So the area I'm looking for is 9 units. P and Q are distinct points on C1 for which R is maximum. Okay, well, I've already worked that out in doing my sketch, in that process of thinking about how to draw this picture, which of course you could have done in your calculators. I'm old-fashioned in that regard. I've already worked these out. So it's r comma theta or theta comma r. I think it's r comma theta. Pi by 4 was where we got our first maxima, and the other is a pi around the other side, or a full cycle around the other side, is 5 pi by 4. Oh, and it still keeps going. The matrix represents a transformation T. T maps a curve onto a new curve, and T maps P onto the point P dash. So we have the coordinate in polar coordinates, 9 comma pi by 4 in polar. Now, matrices only act on Cartesian coordinates. So we need to convert this into a Cartesian coordinate, which isn't too bad at all because we have the polar set up as so. Now this is a right-angled isosceles, so this is going to be 9 root 2 over 2 and 9 root 2 over 2. Oops. So in Cartesian, my coordinates are as so. And then we can hit it with the matrix M. So let's do the transformation. So we're going to multiply that. So I've got that 9 pi by 2, 9 pi by 2 set next to here. So that's going to be one of them plus two of them. So it's going to be three of them. That's going to be 27 root 2 by 2. And the y coordinate is unchanged. Let's try and put my bracket in the right place. And then we need to go back to polar. So now I've got a new triangle here. 9 root 2 over 2. 27 root 2 over 2. And so it's going to be tan inverse of a third. If I'm doing the opposite, divided by the adjacent. And I need to square those and add them together. Oh, so is that going to be... I'm going to have to actually do some work to get to this. I've also changed the pen colour at some point. So they've both got a common factor of 9 root 2 over 2. So I can pull that out, and then I'm left with 3 squared plus 1 squared, which is just a 10, a root 10. This is a problem for not finding my calculator before I started. That's going to be 9 root 5. Find the polar coordinates, and of course you can work out what tan inverse of a third is if you're desperate. It didn't say exact, so I'm tempted to leave it as so, but you should probably work that out. And question 9 keeps going. Find the area enclosed by C2. Okay. Well, that's going to be a little bit awkward. Find the area enclosed by C2. Oh, no, it's not. Not at all. So this, if you actually wanted to do this, is going to be exceptionally difficult. You'll need to try and find the Cartesian equation of the curve, use the matrix to change that equation, and then go back to the polar form to do the polar integral. Or you remember a fact from matrices, and that is the determinant of a transformation is the area scale factor in 2 dimensions. So the determinant of this matrix is 1 times 1. 1 times 1 minus 0 times 2, which is just 1. Which means the area does not change. The area scale factor is 1. And the area before was 9, so the area now is still 9. Slightly worried for a moment, thinking that I had to do some real polar stuff. But actually this was a matrix question. Moving on to question 10. We have everything in centimeters. We have a thin laser pen with 2 coordinates. The laser beam travels from A to B and continues towards a large thin plane of glass. The glass lies in a plane as so, and it hits at an acute angle where alpha is that. Okay, so really this question is telling you about the angle between a line and a plane. We have some sheet of glass. and we have our little laser pen shooting that beam at the glass, creating some angle here, alpha, with the glass. Now, the thing to remember is when finding the angle between a line and a plane, we actually find the angle between the line and the normal. So we actually want to find this angle here, theta. And this is another one of those really cool trig facts. If you have two angles that add to 90, cos of one is exactly sine of the other. So really what the question has told us is that cos theta is root 15 over 75. So now let's just do that method. Let's call the direction of the line AB. So that's B minus A is 2 minus 5, 1. And the other vector we care about is the normal vector 4P 5. So what do we need? We need the modulus of D. 4 plus 25 plus 1 is root 30. The modulus of the normal is P squared plus 41. And we need D dot N, which is going to be 13 minus 5P. Just a quick mental check that I haven't done anything foolish there. So then the dot product formula tells me that 13 minus 5P A dot P is equal to mod cos of the angle. I should probably tell the examiner where that came from. So D dot N equals mod D mod N cos theta. This I now need to try and solve, which is not going to be pleasant whatsoever. Okay, one thing I noticed is I've got a root 30 and a root 15, which is going to leave me with a root 2. And that 15 cancels with the 75, leaving behind a 5, which I can multiply up. Actually multiplying both terms up. Okay, and again, that would you would do that in your calculator. Root 30, root 15 over 75 would give you root 2 over 5. I'm trying to see if there's any way I can not square 65. I think I'm going to have to. So I'm going to square both sides, this side, and expanding out the bracket. Squaring this other side is going to be quite painful. 625p squared. And I think at this point I have to give up and find my calculator, because I'm not going to be able to do this one in my head. Okay, an ancient graphical calculator has been sourced. So back to the calculations at hand. We're getting some unreasonably large numbers. But then again, this question has a context. So having such large numbers is not a surprising factor at all. And of course, that doesn't mean we should just believe everything. It does appear that p itself should be an integer and should be quite nice, which from what we have here doesn't seem plausible right now. These are giving some very unpleasant looking numbers. And if this factorizes nicely, I'll be very surprised, which does mean that I'm going to think a little bit more carefully about some of the other work I've done. And see if I can determine where, if I have made a mistake, where that mistake might be. I'm just checking various of my calculations here and none of them seem so far to be throwing up anything wrong. So let's try and solve this. I'm going to hope that this version of the calculator, and it does indeed have the quadratic solver in it. So let's type in my values. Okay, lovely. So it does give me an integer value of p. So p is 3, or unfortunate, oh, it does give it as an exact, or 1,381 over 623. Yeah, so there's a nice thing. It wasn't just me having a feeling. It does say that p is an integer. So we can just conclude, therefore, that p is 3. Okay, carrying on. A second large sheet of glass lies on the other side of pi 1. This second sheet is modelled by that, so it has the same normal vector, but a different endpoint. Calculate the distance between the two sheets of glass. So these two pieces of glass are parallel, so we can use the trick by going to the origin and adding them up. So if here's my origin, you can find that distance. Also find the difference. If that's my origin, we can find that distance. A distance between this is the square root of. So the distance to the origin was d over mod n for each of them. So the distance between, and this is a formula that I don't really trust so much, but is worth. And actually these are telling me that my picture's slightly wrong, because one's a positive, one's a negative. We kind of have our sheet of glass on either side of the origin. So you've kind of got that distance and that distance. So we're going to have 9 over the square root of 4 squared plus 3 squared plus 5 squared, 4 squared plus 2 squared plus 5 squared. Gives me root 50 plus 5 over root 50. Really, that's a minus 5. So that's 14 over 5 root 2, or 7 root 2 over 5. Distance between the two sheets of glass. The point A, which is the same A as before, is reflected in pi 1. Find the image of A after the reflection. Okay, so we now have a point A. We have our sheet of glass. It's the first time I've really drawn my planes vertical. I normally draw them as horizontal planes, but we can find out where A dash is. So the technique I'm going to use here is I'm going to find the equation of this line. I'm going to work out where it intersects, and then I'm going to double whatever that value of lambda is to go all the way. So I'm going to define the line r equals 7, 2 minus 3 plus lambda, and this is the normal vector 4, 3, 5. And I've got the plane, and we are going to P1, which equaled 9. So that's 4x plus 3y plus 5z equals 9. I'm going to find their point of intersection. So these intersect at 4 lots of plus 3 lots of plus 5 lots of equals 9. And expanding and simplifying that, one of the nice tricks is, because we're using the normal vector for the direction and the normal vector of the plane, the coefficient of lambda is just the modulus of that squared. Doing the other parts, 4 times 7 plus 3 times 2 minus 3 times 5 gives 19. So lambda is going to be negative 0.2. So at A dash, so this is telling me that if we go back to my picture here, lambda is negative a fifth. I've gone negative a fifth of the way. So if I want to reflect to the other side, I need to go that distance again. So at A dash, lambda is negative 2/5, which means the vector OA dash is 7 to negative 3 minus 2/5 of, and that's going to be 5.4. I'm going to write it back as a coordinate because that's what the question wanted. 2 minus 0.4 times 3. And negative 3 minus 0.4 times 5. And that is the image after the reflection. Quite a nice little technique, and it's tempting to try and work out some distances because the distance from the mirror is equal on both sides, but really you just need to think about the lambdas. Question 11. We have a smooth plane inclined. We have fixed points 3.6 meters apart along the line of greatest slope. Particle of mass 0.32 is attached to one end of each of the two light elastic strings. Notice they're strings, so we can't have any compressive forces. It moves along a straight line passing through. The natural length of AP, are the two strings the same? No, we have been told different things about each of them. So we've got L is 1.4 here, and L is 1 there. When the extension in AP is E, the tension is 7E. So I've got a force here of 7EA. And similarly for B, we've got a tension of 7EB. Now, because this is in the pure paper, we're not expected to use Hooke's law in detail. So they're giving us basically what Hooke's law would imply. The particle P is held at a point between A and B, which is 0.2 meters from its equilibrium position and lower. So we're starting slightly lower. At a time t, its displacement towards B from its equilibrium position is x. So the other thing I want to label on is that 30 there. I do have officially a reaction force here. It is smooth, so my picture is complete. This is a 5-mark question, so I can't just write it down. I need to do some work. And the first thing that I want to do is probably find my equilibrium position. Then I'll draw another picture to deal with the general position. So at equilibrium, if I take forces along the line of greatest slope, upwards is 7EA, and that equals 9EB plus 0.32G sine 30. And conveniently, sine 30 is a half. The calculator I'm using is in radians. So that's going to be 7EA plus 9EB, equals 9EB plus 0.16G. We have been told to use G as 10, so I might as well make that 1.6. Okay, but that's got two unknowns. So the other statement we've been given is something about natural lengths. So then A to B, well, the distance we've been told is 3.6. And that's equal to the length in the string of A to P, which is the extension plus its natural length, plus the length of B to P, which is the extension plus its natural length. So EA plus EB is 1.2. Now these are a pair of simultaneous equations to solve. So let's do so. So I've got 7 lots of EA, which is 1.2 minus EB, equals 9EB plus 1.6. Now you should never actually do this, but I'm going to keep going down so I don't have to turn the page. I'm going to have, so I've got 7 times 1.2, and I'm going to bring the 1.6 over. So 6.8 equals, move the 7EB over, 16EB. So EB is 0.425 and EA is 1.2 minus that, 0.775. Okay, so I found my equilibrium position. And now the important thing is we are displaced from that position. So I need to now draw myself a new picture with that displacement in effect. So here's my point A, here's my point B. We are starting below, so this can be my equilibrium position. My object is here. Now, do I want to take up the slope or down the slope to be positive? It's displacement towards B. Its displacement towards B is x. Yeah, so I need to be taking the x to be down the slope. And I've labelled my A and B the wrong way around, haven't I? Yeah. So B is down here, A is up here, x dot is going that way, x double dot is going that way. We've got some forces going on here, and we've got the R and 0.32 G. Now these forces we have to be careful with, because now we know stuff about the extension. So this, the force E, the force up to A was normally 7 lots of. So this one up here will be 7 lots of the extension. Now the extension was at equilibrium 775. 0.775, but I've bought an extra, I pulled an extra x, so that's my tension in A. My tension in B is normally 9 lots of, the extension was 0.225, but now I pulled it towards B a bit, so I've lost the x. So that's my tension in B. Am I missing anything in the picture, or can I F equals MA it straight off? I think I have everything. So let's go with F equals MA. The mass was 0.32, I remember that. So this is going to be. Now I do want to take this way to be positive this time, because that's the direction the acceleration is in, and all the x's are in. So going down the slope, we have 0.32 G sine 30 plus 9 lots of 0.225 minus x but we're subtracting the tension going up the slope plus x equals 0.32, not g, 0.32x double dot. Okay, now if we've done all of the equilibrium position correct, everything should cancel except for the x double dot and the x terms. So you've already done the 0.32 g sine 30 to be 1.6 plus 9 lots of 0.225 minus 7 lots of 0.775. I'm a little worried because that doesn't look like that cancels beautifully. Okay, minus 9x minus 16x equals. So one thing I would want to just quickly check is that also does not work. So what have I misplaced? We have, that's what it is. Misremembered that figure because I didn't turn back and check. So this is 0.425, not 225. So that figure is minus 3.825. And now 1.6 plus that figure. Okay, so that cancels out perfectly. The other issue is I preempted myself with my simplification here. So this is minus 16x equals 0.32 x double dot, and 16 divided by 0.32 does indeed give negative 50. So x double dot plus 50x equals 0, which was what the question required. And that's how these should end up going most of the time. There is quite a lot of work there. You could probably get away with cheating a little bit with the find the equilibrium position, because the astute would notice that this is precisely the formula. It's precisely this formula here. Those two things are identical, so I didn't actually need to find the exact value of EA and the exact value of EB. I just needed that equation equaling 0 to make that thing there disappear. So we could have been slightly more efficient. Part B of the question. Oops. The experiment is repeated in a large tank of oil. During the motion, there's a resistive force to act on the particle, where V is the thing. It caused critical damping. So if we remember what the damping style formula creates, what type of change it creates in the formula, it becomes this. So that damping force appears as a x dot term. Critical damping means we have a repeated root of the auxiliary equation, i.e. the b squared minus 4ac is equal to 0. So that's k squared minus 4 times 50 times 1 minus 200. But no, it doesn't. We need to be a little bit more careful because there's going to be an extra impact on this. So let's go back a little bit further. I was worried because I wasn't getting 16 root 2 over 5 out of that. So if we go back to our F equals MA, we have that the MA equals negative 16x, but now we've got a minus kx dot here, which will then create the equation x double dot plus And if I do 1 divided by 0.32 as a fraction, is 25 over 8k x dot plus 50 x. So yeah, we can't cheat so much. But we could have actually, if your memory was better than mine, you'll recall that this in the term was k over m as the coefficient, not just k. But now we can do exactly the same thing. B squared minus 4ac is going to be equal to 0. So 625 over 64, k squared minus 200 equals 0, very similar to before. So k squared equals 200 times 64 over 625 is 512 over 25. This is making it look a lot happier. And if we square root that, we get exactly what we want. So you do have to go back just a little bit further to put in that damping term rather than cheating too hard. Okay, find x in terms of t, giving your answer in exact form. So now we actually need to go and solve this. So, how many marks? 6 marks. Always worth checking how many marks something is to see how much you can cheat. So I think the best approach here is going to be to write out the equation and just do it, just solve it. We can't cheat too hard. So the 25 over 8k comes out as 10 root 2. So it's going to be x double dot plus 10 root 2 x dot plus 50 x equals 0. So our auxiliary equation is going to be as so. And we know it has a repeated root, which turns out to be negative 5 root 2. So we have our general solution. It's going to be AT plus B, because it's critical damping, e to the negative 5 over 2t. And now I need to go back and think about my initial conditions to work out what I need to sub in. So when t was 0, you'll recall that it was pulled down by 0.2. Particle is held at the point which is 0.2 from its equilibrium, is released from rest. Notice this is the first time that I'm using this 0.2. It's very tempting to have used it earlier in a pitch or something, but that would have been a trap. So those are my initial conditions. So if I sub t equals 0 in, 0.2 equals b. Nice. And if I try to use the x dot, I need to differentiate first. So differentiating this is going to be a bit of a product rule. So I'm going to get negative 5 root 2 when I differentiate the e term. And if I differentiate the other term, I get plus a. And in both cases, the e term just lives. And then using t equals 0, it was released from rest. So that's 0. Negative 5 root 2b plus a. And the e term also disappears. So the b is a fifth. So that kills the 5. So a equals root 2. So x equals root 2t plus a fifth. E to the negative 5 over 2t. Seems reasonable. You could sketch that in your calculator to see if it was particularly reasonable. It is critical damping. When t is 0, I do have 0.2. When t is 0, if I differentiate it and subbed in 0, I do indeed get 0. I can't see anything obviously wrong with that, so moving to the next part. Calculate the maximum speed of the particle. Okay, so maximum speed means I need to differentiate and find my x dot. Now I already have my x dot differentiated without the a and the b in there. I'm just internally debating whether it's worth differentiating it again with the numbers or subbing the numbers into the pre-differentiated. I'm going to sub numbers into the pre-differentiated. So my x dot is negative 5 root 2 t plus a fifth plus the a times by the e to the negative 5 over 2t. So that's exactly what I had before, but I put the a and the b in. Not worth redoing any work. Calculate the maximum speed. So let's simplify this a little bit. So that's going to be negative 10t. That is giving me negative root 2 plus root 2. So it's just negative 10t e to the 5. Negative 5 root 2. Maximum speed occurs when the acceleration is 0. I could have done better than this. Or maybe I couldn't. So acceleration is 0 when you go through your equilibrium point. So maybe I could have applied a slightly more mechanics approach. This is definitely the pure approach. If I differentiate this again, it's another product rule. So I'm going to have 50 root 2t when I differentiate the e term minus 10, which is, so max speed is going to mean that x double dot equals 0, which is 50 root 2t minus 10 equals 0. So t is 1 over 5 root 2, or root 2 over 10. So x dot, the maximum speed, is when I sub that in. It is going to be negative, but then we did expect that. If it's traveling up the slope, down the slope was positive. So this is going to be negative root 2. The 10s cancel. E to the power of 5. Oh, I don't need to do this because I know what t is. Yeah, t is 1 over 5 root 2, and I'm timesing it by 5 root 2. So that's e to the negative 1. So the max speed is going to be root 2 over e. Of course, speed being a scalar, I need to drop that negative sign off. Brilliant. Not a great max speed. That's about half a meter per second. But then again, it is being damped in oil. Question 12. The final question on this paper. Argon diagram shows solutions to z to the 5 equals 1. Solve the equation z to the 5 equals 1, giving your answers in that form. Okay, so that's saying e to the 2 pi, e to the 5 theta equals e to the 2 pi ki, for k is 0 to 4. It's going to give me all my solutions. So my angles are going to be 2/5 pi k, and k equals 0 to 4. So my solutions are going to be, well, when k is 0, that's a boring one. When k is 1, it's cos of 2 pi by 5 plus I sine 2 pi by 5. Cos of 4 pi by 5 plus I sine 4 pi by 5. The next one up is cos of 6 pi by 5. And you can see why I like to use that summary way of writing them for the first couple of lines of working. So if I had to write this out that many times, it'll be madness. Okay, explain why the points on the Argand diagram, which represent solutions, are the vertices of a regular pentagon. Well, they, by z to the 5 equals 1, they lie on the unit circle and are equally spread. And that's what we found in the first part, separated by 2 pi by 5. So I've got, so basically what I've said here is we have these triangles here, which are each identical. They have radius, they have side lengths here of 1, and therefore their final side are also equal, which implies they lie on the unit circle and equally spread, which implies each triangle OZI, ZI plus 1 are congruent, i.e. they're identical, and their final sides, which are the sides of the pentagon, waffling a little bit here, are equal. So I said all the side lengths are the same, all the angles at the center are the same, and their final angles are equal. So they're on a unit circle, they're equally spread, which means each of those triangles are identical, which then means all the side lengths of the pentagon are the same, and the angles in the pentagon are the same, i.e. it's regular. Show that if C is cos, then there's a solution to that equation. Show that if is a solution to that equation, then C satisfies the equation. Okay. So this looks like I'm looking at a real and imaginary parts. So I'm also going to let S be sine theta. So then C plus IS, or Z to the 5, C plus IS 1 equals, and I'm just going to expand this out and see what happens. So it's going to be C to the 5, going to bring up my knowledge of the Pascal's triangle, plus 5C4 IS. Next term is going to be a negative because I've got an I squared, 10C3S squared minus 10IC squared S cubed, times by I again makes it back to being positive, S4 plus IS5. Things to notice is the powers of C decrease, the powers of S is increased. I've got the Pascal's triangle 1, 5, 10, 10, 5, 1. And the I things go 1, I, negative 1, minus I, 1, I. Brilliant. Okay, but then if I look at the real parts, because the imaginary part should just be 0, and the real part is what gives me the C to the 5. I've got C to the 5 minus 10C cubed. Now I don't like the S squared, so I'm going to replace that with 1 minus C squared. And the other real one is the 5c 1 minus c squared squared equals 1. Again, replacing the s squared. Let's simplify. That's 10c to the 5. Now this one you should probably simplify slower. I'm not going to. And plus 5c5 equals 1. Looking at the c to the 5, so I've got 1, 10, 5. That's 16c to the 5. I'm happy. Minus 10 and minus 10c cubed. Also happy. I've only got a single c term, and I can bring the 1 over as required. A very, very efficient 5 marks. If you're super comfortable with your Pascal's triangle and basic algebra. The diagram is repeated. Explain why why that expression has a repeated quadratic factor. Okay, well, this is giving me the real parts. So the solutions are the real parts of Z1 to Z5. And from the picture, we have that the real part of Z2 equals the real part of Z5. They're on the same vertical line. And the real part of Z3 equals the real part of Z4. So the quintic has 2 repeated pairs, which implies it has a repeated quadratic factor. If we put those pairs together, then we create a quadratic. So the quadratic with solutions Z2 and Z3 is the same quadratic as the solutions with Z5 and Z4. And just to make that real obvious, C minus the real part of Z2 and C minus the real part of Z3 is equal to the real part of Z5, C minus the real part of Z4. They're both factors and they are repeated. Okay, O is the center of the regular polygon, of a regular polygon. Okay. And H is the distance from O to AB. So this is now pretending to be a completely different question, but really is, well, by treating it as complex numbers, we get a nice solution. So we have now, we're calling this pentagon ABCDE, where all of them from the origin are center of 1. The distance from O to AB is H. O to AB. Well, I'm going to cheat. I'm going to call AB this one. So this distance here is going to be H. So this is my A, B, C, D, E. It might have been tempted to call AB this one, but then H is at a weird angle, and that's just foolish. So I'm going to choose H. I'm going to choose to label as so. Then H is just going to be the real part of Z3, which is going to be the negative solution of that quintic. So I now want to solve this quintic. Now it is a show that, so I can't just put it in my solver, but we already know some stuff. We know it has a repeated quadratic factor, and we know one of the solutions. Because of point D, because of Z1, which has a real part of 1, z1 is just 1. We know that c minus 1 is a factor. So let's factorize out that thing. So c1 leaves behind 16 c to the 4. What's the next term? We've got minus 16c to the 4, which I don't want, so I need to add 16c cubed. I've got minus 16c cubed, but I want minus 20, so I need to subtract off another 4c squared. That gives me a positive. That gives me positive 4c squared, which I don't want, so I need to subtract off 4c. That gives me a positive 4c, but I want positive 5c, so I need to add 1, and then the 1 times the minus 1 works. Okay. Now that 16c to the 4 plus 16c cubed thing is a repeated quadratic factor. What is that repeated quadratic factor? So what is this saying? It's saying 16c to the 4, then part D is going to imply this thing is 4c plus 1 is equal to, and I should really use different letters, alpha x squared plus beta x plus gamma times by alpha x squared plus beta x plus gamma. So what are these things? Well, it appears, it looks like alpha should just be 4. So how do I wish to do this in the most sensible way? Alpha can be, we can make alpha 4. Really, it's plus or minus 4. But if it's minus 4, then we'll just swap all of the signs. Now, the thing we need to be careful is then we can't also assume that gamma is positive 1. Because gamma could be plus or minus 1, and then that makes a difference. So I'm actually going to expand some of this out to see what happens. So if I expand out that term, I get alpha squared. If I look for the cubed terms, I'm getting 2 alpha beta x cubed. That will find me my beta once I know my alpha. So that really means I should always also look for my x squared term, which will be alpha gamma, 2 lots of those, plus beta squared, x squared. I don't care about the rest. I might find them later as a checking technique. So that means that alpha we can pick to be 4. 2 times 4 times beta is 16. So that's 8 times beta. So beta we can choose to be 2. And then finally 2. So 2 alpha gamma is going to be 8 gamma plus 4 equals negative 4, which means that gamma is actually going to have to be negative 1. If we just made that assumption before, then we would have missed that. So that means, and I'm going to call this equation star. Star is then c minus 1, 4c squared plus 2c minus 1 squared. And if I do check, I made a sign error here. I was just suddenly worried because if I expand out that quadratic-y thing, I'm getting a minus 2c, should be giving the minus 4c as I wanted. Okay, so this is still equals to 0. So let's now solve. So that means that c equals 1 or 4c squared plus minus 1 equals 0. So c equals quadratic formula time negative 2 plus or minus the square root of b squared minus 4ac, which gives me root 20. over 2a. And let's simplify that a little bit. That'll be minus 1. I'm pulling out a factor of 4, which turns into a 2, plus or minus root 5 over 4. And now this goes all the way back to what my picture was. H is the negative real part of Z3 or Z4. So then the real part of Z3 is the negative solution to this, minus 1 minus root 5 over 4. So that implies that H is the negative part of Z3, which is root 5 plus 1 over 4, as the question required. Quite an unpleasant last part if you don't notice how to use that H in the right way, how to interpret, let's say, that H in the right way. Quite a lot going on with that one. But that is the June 2022 paper complete. Only 12 questions, but there were some really big ones in there. Question 12 itself was almost 20 marks. Question 11 was almost 20 marks all on its own. If you have noticed any errors or any omissions, please do let me know. And hopefully this was quite a useful discussion and walkthrough of this entire paper. So, happy revising and enjoy the rest of your day.